All right, so today we are graphing tangent and cotangent. And it's important that you have a basic understanding. The most important graphs are sine and cosine. And if you know those, that's really, really good. Tangent and cotangent are a little different. And then tomorrow we'll do secant and cosecant, which are based on the sine and cosine graphs. So if you know how to graph those, then secant and cosecant are really easy.
Are they just like opposite?
Well, they're reciprocal. So we'll talk about that tomorrow. Today is tangent and cotangent, and they're a little bit different than all the others. And so using your calculator can be really, really helpful. But again, it all comes from the unit circle. So here we go. We'll come back to it. Forget this. Don't like that.
Is example 1?
No, it's graphing tangent. So let's graph y equals tangent of x. Looking at the unit circle, you do not have to write all of this down. So we're going to graph y equals tangent of x. So to do tangent of x, I guess we'll start by making a little xy chart. Tangent of x equals y. And again, we have our little unit circle picture here. And we are starting, I'm going to start here where x is 0. And we want to figure out the tangent. Well, at 0 radians, what ordered pair are we sitting at? Almost
1, 0.
1, 0. How do you find tangent? Y over x, the y coordinate over the x coordinate. Or you could think sine over cosine. We've talked about that as well. So if we wanted to do tangent, then that would be 0 over 1, which equals 0. So we have the ordered pair 0, 0 that we can graph. So tangent passes through the origin. That's good to know. Let's come up here just a little ways. This is pi over 4. What's the ordered pair at pi over 4? Radical 2 over 2, radical 2 over 2. And again, if we want to know tangent, how do we calculate the tangent at pi over 4? Y over x. Yeah. What is radical 2 over 2 divided by radical 2 over 2? 1. Oh, okay. So at pi over 4, we have a value of 1. Okay. Let's come up here to pi over 2. So we want to know what's the tangent at pi over 2. So the ordered pair is 0, 1. Yes, you are correct. And so then how do we calculate the tangent at pi over 2? 1 over 0. When the 0 is under, it's undefined. All right. Graphically, what is it when something is undefined?
Asymptote.
An asymptote. Very good.
I thought you were just saying the letter.
All right. So at pi over 2, we get a vertical asymptote. That's very, very good. That's interesting. I think I want to go on the other side here and see what's happening to the left. So I'm actually going to go with some negative angles here. Let's see what happens at negative pi over 4. So here is negative pi over 4. I want to know what is the tangent at negative pi over 4.
Negative radical 2 over 2 divided by radical 2 over 2.
Good. Yeah, the ordered pair is radical 2 over 2 and negative radical 2 over 2. So tangent would be y over x or sine over cosine. So negative radical 2 over 2 divided by radical 2 over 2, which is negative 1. All right, so at negative pi over 4, we're at negative 1. And then down here at negative pi over 2, what do you think? Undefined. It is 0, negative 1. So if we were at negative pi over 2, it's going to be undefined again. So I'll mark that down. Negative pi over 2 And the zero's under, it's undefined. And it turns out that if we were to keep going around, if I went to 3 pi's over 4, my tangent value would be -1. Bless you. At pi, tangent would be 0. And at 5 pi's over 4, tangent is +1. And at 3 pi over 2, we're back to undefined. And we could keep going around and around and around that unit circle, but this is the tangent graph. It just looks like a little stretchy ass shape. It's kind of like a cubic. And this is the shape of tangent. It's not really an S, I know.
Oh.
It's not.
Yeah.
Okay. So you can graph it in your calculators. You can type in bless you tangent of X. I don't know what it is with this class. This is absolutely ridiculous how many sneezes there are. Every day. It's like sneeze central.
Sorry about that.
Okay. So now here's the question, ladies and gentlemen. This is the tangent graph. Very different than sine and cosine, right? Yeah? Okay. So the question is, what is the length of one period?
When it has the in between the undefined.
In between the undefined, yeah, in between the asymptotes, that's the length of one period. So this is one cycle, and then it repeats itself. So there's one period. How long is it?
Wait, what do you mean?
How much time does it take?
Pi.
Pi. How did you get pi?
Well,
There's a lot.
What if you went for this one? Here's one period.
oh, it's because
Because it's the middle of the face.
How much is in between?
They're both from each other.
Okay, when you subtract, sure. If we were to take here, it ends at 3 pi over 2. So 3 pi over 2 minus pi over 2 is 2 pi's over 2, which is just pi. The same thing is true if we look at this this period that is right around the origin. If I were to subtract pi over 2 minus the negative pi over 2, what happens? Oh, the minus the negative becomes plus. So we get 2 pi's over 2 again, which is pi. The period is pi. What's the period for sine and cosine? 2 pi for the standard functions. Good. Okay. So that's nice. What we really need to know about the tangent function is the normal starting and ending points. So this, I'm going to say, is our normal start here at negative pi over 2 and our normal end. And what those starting and endings are on tangent are asymptotes. So that's something you need to know. It normally starts at negative pi over 2 and ends at pi over 2. And those are asymptotes. And there's 3 things in between. Okay, sort of a low, middle, and high. The tangent function is an increasing function. It's going uphill from left to right. I like to think about it as toes to nose. Low to high, toes to nose. Is that, yeah? T, toes, in, nose, toes to nose. And if it's Spanish, toes to nose. I don't know what toes is in Spanish, but is too, right? So, okay. Well, nariz is nose. I don't remember what toes is. Okay. Toes to nose. All right. Here's what's really important. We need to talk about the asymptotes. We have vertical asymptotes You can see right now we have a vertical asymptote at negative 1 pi over 2 and 1 pi over 2 and 3 pi over 2. Where's another vertical asymptote going to be at? 5 pi's over 2. Where's another? 7 pi's over 2. 9 pi's over 2. All right, 11. Okay, very good.
The odd ones.
The odd ones.
Yeah.
Okay, that's really important. These are odd. We call this, I need a way to say all that in a nice, compact way, a mathematical way to describe all of those.
Those are odd.
So a vertical asymptote is always the equation x equals, and all of these have some number in front, but they're all multiplied by pi over 2. So I'm going to call that number in front k, pi's over 2. And we get to describe k, where k is, what did you tell me about k? It was odd. Well, it's odd. It's what we call an odd integer, where k is an odd integer. What are integers?
Positive or negative, rational, whole numbers.
Whole numbers. Positive and negative whole numbers. Integers are negative 2, negative 1, 0, 1, and 2, and on and on and on. Integers are the positive and negative whole numbers. And so we can describe every single asymptote as k pi's over 2, where k is an odd integer.
But there's not one that one pi over 2. There's not one.
Yeah, so it's 1 pi over 2?
Oh, there's.
Yeah? Okay. Good. You're good. And negative 1 and negative 3 and negative 5. So odd integers is the very specific way to describe the value of k. So once you know that, what's the domain of this tangent function?
Negative.
All real numbers except x equals k pi's over 2, where k is an odd. Yeah, everything except those asymptotes.
Oh, wait, domain.
Wait,
I
how
was
do you
thinking,
draw that?
I was thinking range.
That's R. It's
Yeah.
it's basically just an R with two vertical stems. That is R for reals. All real numbers. That is the mathematical notation for the real numbers. Everything except those asymptotes. Everything except x equals k pi's over 2, where k is an odd integer. There's also a special symbol for integers. I just can't remember it. I can look it up. I have the book still, but I told pre-cal I'd look it up, and I never did either. So, range. What's the range of the tangent function?
Negative infinity to infinity.
Yes, forever the down and forever up. So all real numbers there. And if you want to put just the big fat R, big fat R. That's funny. Sorry, the real numbers, you can do that as well. Same thing. Okay. The big important thing that you need to know is that the standard graph of tangent starts at negative pi over 2 and ends at pi over 2. Wow, you can't see that now, but you can remember it. That's what you need to know for when we graph. Also, it's increasing, toes to nose, toes to nose. Okay, let's look at cotangent. So we're going to graph cotangent of x. We're graphing cotangent of x. Zero, pi over 4, pi over 2, 3 pi over 4, pi. Okay, that's good. Let's walk around our unit circle again. Starting at 0 radians. I'm at the ordered pair 1, 0. How do we figure out cotangent? It's a reciprocal. So that would be the x value over the y value, which in this case, if we did what's the cotangent at 0, that'd be 1 over 0, which is undefined. Oh, so right here at 0, what do we have? An asymptote, yeah. So a vertical asymptote right on that y-axis. Right off. Here at pi over 4, we are at radical 2 over 2, radical 2 over 2. What's cotangent? Still 1. Pi over 4, 1. At pi over 2, the ordered pair is 0, 1. What's cotangent going to be? 0 divided by 1, which is 0. Okay. At 3 pi over 4, we have the ordered pair negative radical 2 over 2 and radical 2 over 2. What's cotangent? Negative 1. And then at pi, we're at negative 1, 0. What would cotangent be? Undefined, yeah. So negative 1 over 0, x over y. Again, that's undefined. So we get another vertical asymptote. Jack, which question?
So for the last one, like you said the starting and ending, which does it start on? Does it start on like negative?
For tangent, negative pi over 2 and positive pi over 2. Yeah. All right. So what do you think cotangent looks like?
The opposite.
Yeah, it's flipped. Flipped upside down. Yeah, it is. Yeah, so it's flipped. Yeah, so this is one period of our cotangent function. So it's flipped upside down. How do you type this into your calculator is a good question. 1 over the tangent of x is how we plug that into our calculator, and you can see it graphed there. So this is also not centered like tangent was. It does not pass through the origin. And so it's shifted over a little bit. Thank you. Oh, you know what? She is absent. Here you go. And again, it does just repeat. Cotangent is a decreasing function. Where would the next asymptote be? If it's at 1 pi, where's the next one? 2 pi.
3 pi. All the whole numbers.
3 pi is another asymptote.
Whole
What else?
pi.
4 pies. All right, okay. All right, so how do we write all the vertical asymptotes then? Where do they all occur at? Whole pies. That's really good. X equals, you can see we have a 1 pi, a 2 pi, a 3 pi, a 4 pi, some value of k times pi, where k is, so is it just whole numbers? Over here be negative pi is an asymptote. So whole numbers, the whole numbers start with 0, 0, 1. I talked about that the very first day of class. Whole has a 0 and a 1 in it, right? Do you remember that? That 0, 1, 2, those are the whole numbers, starting with 0.
Oh, yeah.
Integers, that's right. So we want where k is an integer. Integers include the negatives as well. So we want to include those negative values as well. Okay. The domain for this is all reals except those things. Okay. So I'm drawing an arrow. All right. All reals except those asymptotes. So, and the domain is, the range is negative infinity to positive infinity, or the reals again. All the possible y values. What do you need to remember from cotangent? The starting and ending points. Again, the period is a length of pi. It starts at 0 and ends at pi, and that's what we need to know. For one regular period of cotangent, it starts at 0 and ends at pi. And if you can remember that, those starting and ending values, then you can graph these things really easily. Cotangent is a decreasing function. It's going downhill. I like to think about cotangent as a coat, as like putting on a coat. When you wrap your coat around you, it drapes over your shoulders first and then falls around your legs. So that's how I think about this, as shoulders first, high first and low. I don't know. But that's what I think about. All right, so now you know the basic graphs of tangent and cotangent, and now we're going to graph just a couple to get an idea here. Example 1, sketch the graph of the function. Sketch the graph of the function, and again, whatever the directions are in the book, you're going to graph it like I do. Okay. State the domain and range and asymptotes. Good practice is really what that is for. All right, so first, this is the cotangent graph. What does this 3 do to it? It makes it taller. It stretches it vertically. That's good. And so instead of 1 and -1 vertically, we multiply it by 3. So there'd be 3 and -3 vertically on the graph. So we'll talk about that in just a second. But this stuff inside with x is going to change those vertical asymptote locations. So everything inside with x, that's what we use for our starting and ending. So where were the starting and ending points on the cotangent function? Where were those first asymptotes? 0 and pi. All right. So on the original cotangent, had asymptotes at 0 and pi, but when we have stuff inside with x, that's going to cause some changes. So just like we did with sine and cosine, we need to solve for x. How do you get x by itself? Divide by pi. Good. So 0 divided by anything is still 0. Oh, pi divided by pi is 1. So I am going to have an asymptote at 0. There is a vertical asymptote. And at 1, we have a vertical asymptote. Well, 0 happens to be my y-axis. It's going to have multiplied by 3. So 1 times 3 is 3, and -1 times 3 is -3. Now we have our 0 for our starting and our 1 for our ending. I'm going to subdivide that just like we did with sine and cosine. What's halfway between 0 and 1? 1/2, or 0.5. And then what's halfway between 0 and 1/2? 1/4. Half of a half is 1/4. 1/4, 2/4, 3/4. Okay. This is the cotangent function. What shape is it?
It's going
Coat. High, middle, low. Top to bottom. Okay. Coat. Putting on your coat. High, middle, low. That's a great graph. You can imagine if we have asymptotes at 0 and 1, where's another asymptote going to be?
2.
At 2 and 3 and 4. All right, so how do we describe all these vertical asymptotes? X equals 0 and 1 and 2 and 3 and 4. X equals... are there asymptotes to the left?
Yes.
Yes, so integer. X equals k, where k is an integer. Very good. Good. That's really, I think, if you can be able to write that, that's really, really good. There's good vocabulary in that, and that's really good thinking. Okay. The domain would be all reals except that stuff. So I don't want to write it down. The range is all real numbers, so that's okay too. All right, this is a great graph. That's all I want to see. Do you have questions for me on the first one? Okay. How do you check it in your calculator? Because so how do you type this in is the question.
1 over.
Oh, 1 over 1 over 3.
So careful. This is 3 times cotangent. 3 times cotangent is 1 over tangent of pi x. Okay, and so yeah, so we can't put 1 over 3 tangent of pi x because this is 3 times 1. You could say 3 over. So I'm going to type it in 3 over the tangent of pi x. That's the most compact way to write that. 3 over the tangent of pi x is the most compact way to write that. And I'm going to change my window. I want my window to go from 0 to 1. And my y-axis, I don't know, -5 to 5 is probably fine, or -4 to 4. Something similar to what I have drawn. And there you go, that's pretty good. Okay, if you wanted to see more, we said there were asymptotes every integer. So there's an asymptote at 1, asymptote at 2, asymptote at 3, asymptote at 4, and an asymptote at 5. All right? All right, one more. What does the negative do to our tangent graph? It flips it, okay, and the 2 stretches it. I'm going to take everything with x and figure out where the asymptotes are. Where were the starting and ending asymptotes on the tangent function? -pi/2 and +pi/2. Very good. Again, it's different. You see the changes? These are the things that you have to remember. All right. I need to get x by itself, so I'm going to go ahead and add pi/2 to both sides. -pi/2 plus pi/2 is 0. 1 pi/2 plus 1 pi/2 is 2 pi/2, which is pi. All right. So I have an asymptote at 0 and an asymptote at pi. Where's another asymptote going to be? 2 pi/2, which reduces to, yeah. 1 pi/2 plus 1 pi/2 is,
Yeah.
Swear to God, this is.
are you okay? There was a lot of chatter just now. You figured it out now? You with me now? Oh, you can't see? 1 pi/2. So I'm adding the pi/2. Adding pi/2, adding pi/2. Negative pi/2 and positive pi/2 is 0. Cancel that. Here, 1 pi/2 plus 1 pi/2 is 2 pi/2. And the 2's reduce. Pi. Yes. All right. So I'm at 0. That happens to be my y-axis. I have a vertical stretch of 2. I just need to subdivide. What's halfway between 0 and pi? Pi/2. What's halfway between 0 and pi/2? Pi/4. 1 pi/4. 2 pi/4. 3 pi/4. All right, so this is tangent. Tangent normally went toes to nose. Low, middle, high. So that was the normal shape of tangent, but this one's been flipped. So it's going to be high, middle, low. All right. And you can totally plug this one into your calculator pretty easily. -2 tangent of x minus pi over 2.